Morning, everyone. I'm Leiden University. Today we have Reinout Quispel from the Trobe, who's been leading us through the end of next week.
Okay, well, thank you very much. It's very nice to be here and speak in front of a live audience. First time in 18 months, I think. So it's great. And of course, I'm also happy for the, if there's anybody listen. We have some people remotely. Okay, that's great. Well, welcome to you as well. So today I'm going to be talking about how one can find properties of differential equations. Actually, the whole talk will be about the properties of ordinary differential equations and how you can preserve those properties under discretization. And those two questions are sort of going to be the two halves of the talk. And actually, they're going to be done in the opposite order than the title. On the first slide, you see my collaborators over the years. Some of them are at my own university, the Trobe University. Some of them are in Norway at the University of Technology in Trondheim. And then there is Giorgio Gubbiotti, who actually used to be here at Sydney University and is due to go to the University of Tokyo. And there's Andy Hone, also a well-known person here in Sydney. And let's see, and then there's Robert McLaughlin, and who I worked with very much over the years from Massey University. Okay. All right, so the first, I'm going to give a very brief intro. And then once that is finished, I will talk about two parts. First part will be if we are given an ordinary differential equation that we know has certain physical or what we call geometric properties. So you can think of energy, preserving, volume preserving. Anyway, you'll see that on the next slide. How can we preserve those properties under discretization? And in the second part, we're going to be talking about opposites. If you have an ODE and you have discretized it in the proper way, so properly to be defined in the talk, then how can you find properties of the differential equation from its discretization? It turns out that sometimes it's easier to first discretize and then find the properties of the discretization and then take the continuum limit in order to find the properties of the differential equation. So I'll start now with the introduction. So my research over the years has mainly been in two disjoint areas. One of those is discrete integrable systems, well known to people here in the audience. Of course, Nalini has written a whole book about discrete integrable systems. And the other area that I worked in is geometric numerical integration, which is really to do with the numerical integration of differential equations. But there, the idea is that you preserve a certain property of the differential equation. So that blob of GNI, which is the geometric numerical integration, that contains things such as symplectic integration methods, energy preserving integration methods, volume preserving integrators, symmetry preserving integrators, etc., etc. And usually there are different methods for each different property, and it's very difficult to combine more than one property at once for a general case. Of course, for special cases, things may be possible. And then, of course, discrete integrable systems that contains the so-called QRT maps. We have Q and R here in the room at the moment. Discrete Manabé equations, discrete soliton equations, etc. So, over the years, I worked in each of those areas, but they were completely disjoint. So the collaborators I had in discrete integrable systems, they were different from collaborators in geometric numerical integration. And So I was sort of a little bit schizophrenic, you might say. Then about 10 years ago, that we realized that actually the intersection between these two areas was not completely empty. But there were some methods in the middle, in the overlap, if you like, which I call for the purpose of this talk, birational numerical integration of the ordinary differential equations, that combine the two notions in a sense. So this intersection, the B and I block, that contains the so-called Kahan, Hirota, Kimura method, and that name itself already is sort of like a symptom of the fact that it belongs to the two areas, because Kahan very much is in the geometric numerical integration, and he discovered this method in around 1970, and then something like 20 years later, this was rediscovered independently by Hirota and Kimura, who were interested in preserving integrability. So, and whereas Kahan was interested in numerical solution of differential equations. So, two different people or different groups discovered this method, or the main method that I'll be talking about today, that will turn out to be sort of birational numerical integration method. There are other ones which I've written here on the slide. So the polarization methods, some methods by Andy Hone with a little help from myself, and then there are ad hoc methods which are tuned to a specific differential equation. For instance, the Mickens has written a whole book about that. So these birational numerical integration methods, they actually can combine the preservation of integrals as well as phase space volume, and even in some cases complete integrability. And so we will see that in the rest of this talk. Now, most of you, or some of you at least, will probably not know who Kahan is. So I will show you. This is a photo a little while ago, because he's close to 90 at the moment. And he's actually a very well-known guy in computing. He won the 1989 Turing Award for his fundamental contributions to numerical analysis. Now, for those of you that don't know what the Turing Award is, it's sort of the Nobel Prize in computer science. And currently the prize is $1 million. Probably not when he got it. Berkeley. But he is Canadian. He's been in Berkeley forever. So in this talk, I'm going to be talking, well, my example will be the Kahan method. And in 1993, Kahan wrote about what we now call the Kahan method. Is I have been using these methods for 24 years without quite understanding why they work so well as they do when they work. So I guess the point is they work under certain conditions, which were not known what the conditions were at the time. And then the question is, when those conditions hold, what actually is happening? So those questions we have been trying to unravel for the last 10 years or so. So in this talk, I'm going to have two main examples to exemplify what we're talking about. And this will be my first example, this differential equation number 1. And that's a two-dimensional example. I have two variables. And of course, we're interested here in nonlinear. And so this is also should express that this is a quadratic differential equation. Kahan's method is defined particularly for quadratic differential equations. So how does the discretization work? Well, in equation 2, you see that the time derivative, you use completely standard differential, discretization, and where I use the shorthand x prime, that just means x after n plus 1 time steps, and x is x after n time steps. And h here is the time step, that's sort of standard. You can think of that as delta t or tau. So then in equation 3, we define the discretization of the linear parts, and in equation 4, we define the discretization of the vector parts. And the important thing about the equation 2, 3, and 4 is that you see that they're all going to be linear in the new points, so the x primes. So that means that even though in equation, once you substitute 2, 3, and 4 in equation 1, even though the x primes are going to be on both sides of the equation, they only appear linearly. So we have to solve a linear set of equations to know what the new point is in terms of the old point. And so that is almost as well, it's virtually the same as being explicit, and actually we'll write down the explicit formula. But not only that, but also vice versa. If you're given the new point, then you can find the old point also by linear method. So that means you solve that, you get a rational expression. So it's rational in both directions. And that's by definition, that's birational. So this defines a birational method for quadratic expression. And so if we do all of this to our equation 1, we get the following result. So here on this slide, first of all, so when you look at this, the left hand side describes the differential equation. First the phase plot, then the equation, then the preserved integral, and then the density or the preserved measure. And then on the right-hand side, we have the analogs for the mapping. And the mapping, which I will call in this talk phi, is given by x prime, is the phi h of x. And I haven't written it down here. I hope it will still come later on. But it doesn't matter really what it is exactly. It's easy to find out. And there, the integral, now it has become a rational function. And I just used the shorthand h in the numerator because otherwise it doesn't fit on the line. So the whole point is that the numerator is a cubic function, the denominator is a quadratic function. So this is a big difference. The differential equation in this example has a quadratic integral, has a polynomial integral, and the mapping, discretization, has a rational integral. That will be important in the future because it means that if we have the differential equation and we apply this method, we don't have the identical preserved quantities. The method is the differential equation is integrable, and so is the mapping. So in that sense, they're both integrable, but the precise features of the integral is different in both cases. So that means even if we know what the h is, it's not obvious what this correction term here with the h squared, well, 2 point, because people can't see that, but the h squared term is going to be. Actually, later on, it will turn out we have found formulas for this. But when you first do this, you can it's easier to find in examples rather than some completely general formula. That's sort of the way these things work. But first, you find some special cases, and then you do so this is if you like the special case. Yes. Yeah, I think that is you're certainly right. So this is called the H wiggle. So that's another thing in the talk. I'm trying to represent the discrete properties with wiggles. Now this decided this at the last moment, so that may not have happened everywhere, but and they're called modified. And because of these H squared terms, they're not identical to what we got. And actually, it doesn't always have to be H squared. There can be more terms in the H expansion. This is a special case. And I think you're right. And of course, if you look at the phase plots, that's why I've done this also. They look remarkably similar, right? However, if you go further away in phase space, they're actually going to be different because the H wiggle, as you see, has a singularity, which the H has a singularity at infinity, but H wiggle has a finite singularity. Actually, if you look closely at the denominator there, you see that there's going to be a circle with radius something like 1 over h, where things go, where we get a singularity. Now, of course, if h it's small, and 1 over h is large, so the circle is very far away. As h goes to 0, the singularity goes to infinity. So then, because of the fact that they're not identical, then here, as you said, there's a new. And I must say also this definition of modified, sometimes in numerical integration things are called modified when they're not exactly preserved. But here they are exactly preserved, but it's a different quantity that is exactly preserved. Okay, so this was my intro. So the rest of the talk will be 2 parts. How do we find these quantities that we just saw, the H wiggle and the M wiggle? And in the second part, I'm going to questions. How can you use the Kahan discretization to find properties of the ODE that you didn't know from the beginning? Because just to go back, I never used the expressions for H in the definition of Kahan's method, right? So Kahan's method, in a sense, is what we like to call in numerical integration foolproof. It preserves things even if the user doesn't know that it has those properties. But in many cases, of course, we do know that we have a Hamiltonian system, and then we want to. Okay, yeah, the other thing is what I stress. I talked about, for instance, in part 2, hard to find properties. Right? For the purpose of this talk, rational integrals would be hard to find, and polynomial integrals easy. The reason being that finding polynomial integrals is a linear problem. Linear is a coefficient of the polynomial, whereas rational is a non-linear problem. But to make a long story short, this talk is going to turn finding the rational integral also into a linear problem. That's sort of the crux of the matter, which we can do for the discretization, but not for the differential equation. All right, so here is part 1. So remember that in this 2-dimensional example, that these were our H wiggle and M wiggle, so the discrete preserved quantities. And we see that. Of course, H wiggle is rational, but that means it's a ratio of 2 polynomials. And M wiggle is 1 over a polynomial. Now, in this case, it happens that the denominator of H is the same as the denominator of M. That's not always the case. But so we have, in a sense, we have to find these 2 polynomials. So how do we find these 2 polynomials? So the numerator of H and the denominator of H, which is the same as M wiggle. Well, after we've been working in this area for a fair while, we discovered, and actually pointed out to us by Bambos Creepy-Doo, that these polynomials are so-called double polynomials. Since I might say they're discrete double polynomials. And because really, there had been very little work on discrete double polynomials. The main body of work for double polynomials is for the continuous case for ordinary differential equation. So I'm first going to explain what double polynomials are for the case of differential equation and then for mappings. Okay, so this is a little bit of a full slide. So we are given we have a polynomial vector field, then P of x is a double polynomial, and there are also lots of other names for double polynomials: second integral, weak integral, special integral. These different names. So okay, so P is a double polynomial for the differential equation of the vector field if there is a polynomial function C such that the PDT, I use the dot for the time derivative, the PDT equals C times P. And there, of course, this equation 5 should hold for solutions of the differential equation. So the PDT is PDX times dx and t. So that's gradient of P dot product with the vector field F. And the function C is called the cofactor. C. So this is a sort of a generalization of the case for integrals, for first integrals. If C is identically 0, then we have then P is an integral. First integral. Now, for this double polynomials, weak integrals, or second integrals, you see that if P equals 0 at time 0, then it stays 0. So you get a subset of phase space, but not every phase space is not foliated. So 1, 2, and 3 here are some simple cases. If C is identically 0, we get first integral. If C is a constant, it doesn't depend on x, then we can solve equation 5, and we get that P at time t, if you like, is P at time 0 times e to the ct. And that is something that is frequent. And then, important case is also the cofactor equal to the divergence of the vector field. Then the equation 5, the solution of that gives the preserved measure, which is then 1 over dx over p. And some simple properties of cofactors are the following. Because of the product rule, you have that the cofactor of the product is the sum of the cofactors. And that's equation 6 here. And from that, it also follows that if we have two, let's first go to the next slide. So here we have the generalization of that. Let's say we have n double polynomials p sub I for I 1 to n, each with a different cofactor. Then the cofactor of product pi to the alpha I. It's going to be the sum of linear combination of the cofactor and then sum. Okay. So now the point is, if this linear combination of cofactors is going to somehow manage to get that equal to 0, then the left-hand side will be the integral. Right? And so that's the game. And you want to find as many double polynomials as possible, and then try to combine them in such a way that you can. But then you first have to find the double polynomials. Say, 8. We first have to know what the CIs are. And we don't know what the CIs are. So we try to solve for 2 things at the same time. My guess is that this is one of the reasons that double polynomials are not used as much as I guess you might like. Because it's not that easy. In low dimensions, there are some theorems, but in higher dimensions, it's not that easy to find both C and P, and then essentially you have to find sufficiently many that you get linear combinations for 0. For instance, the simplest way to do that is you have 2 double polynomials with the same cofactor, and the ratio is going to be. Okay, so now we're going to look at the discrete case, the analog of discrete case. So now we have the mapping, instead a rational map, and now we define a discrete double polynomial, which is indicated by the wiggle, to be discrete polynomial. Two polynomial if the wiggle of x at time n plus 1 is c wiggle times p of x at time n. Now, the one difference of the p's are polynomials, but one difference with the differential equation case is that you get interesting cases, you have to take the cofactors to be rational functions now. Because to get interesting maps, you have to take the phi rational. So that means as soon as you have an xn plus 1, you're going to get a rational expression. So you're not going to get very far if you restrict the C wiggles here to okay, so now, as I said, we use the shorthand function notation. The prime for the loop point and the unprime for the whole point. And here I wrote down it's the same for the discrete case as it is for the continuous case. The ratio of 2 double polynomials with the same cofactor is going to be an integral. And more general, now we're going to have a product of double polynomials, same product as we had before. Product of the p's like that is going to be an integral, but now we're not going to get the sum of the cofactors, we're going to get a product of the cofactors, and so it's not the sum is going to have to be 0, but the product is going to have to be equal to 1. And so in a sense, a very much here in sort of the group case, whereas the differential equations correspond to, or the cofactors correspond to the algebra case. So, and now, but of course, we have to still have the same thing. If we look at equation 10, if we want to find both the p wiggle and the c wiggle, we have to solve for 2 things. It's still going to be very difficult. However, if we know what the c wiggles are, or we have a good guess of what the c wiggles are, then equation 10 is still a linear problem. So that, and actually, it turns out we do have a good idea of what the c wiggles might be. And that is the next slide. Jacobian vector ansatz. So we have a rational map. Calculate the Jacobian. Sorry. The Jacobian determinant, and that's the to calculate derivatives of the new x's with respect to the old x's. That gives you a matrix. You calculate the Open of that matrix, so that's all defined by the Arts method, and then you factorize that determinant. Now, of course, if you want to do that by hand, it gets literally out of hand very quickly. But for Maple, this is a very simple problem, at least. 10 dimensions, it's not a problem. And then the ansatz lecture is that building blocks of the cofactors are the factors. You can have different exponents that don't all have to appear. Numerator of the case, the bottom power, and the date with the deeds to some power, and we have this concept is the same in the cofactors, except the exponents. So, and of course, the number of factors in the cofactors is finite, actually. Sometimes there's only one in the numerator and only one in the denominator, so that it's not so difficult to find. But of course, it might still have to reach some higher power. But still, in general, it will turn out that this finite number, checking a finite number is enough to find all if you want for your given problem. And the analog, of course, divergence of the vector fields, Jacobian determinant. So in the discrete case, if you discrete cofactors equal to Jacobian, then you find the preserved measures. So if you can solve that equation, if there are solutions, of course there are not always solutions, not every system is measure preserved. Okay, so now we're going back to our two-dimensional example. Cubic Hamiltonian. The question is, how do we find the best? Well, to recall the first, we just take the Jacobian itself as a cofactor. Do that because then you can at least find the preserved measure. So we know what the Jacobian is. Then we just make the ansatz for the p wiggle for the taboo polynomial to be a polynomial. Just take every monomial up to third degree. And then we have to find these coordinates A, B, C, D, E, F, G, H, I, J. So that's, we ask our good friend Medical or Mathematica or whatever you want to use, or used to using, to solve this, and it gives the following answer. First line here. So it turns out actually that and that's the beauty of something like Maple. It gives it in this form as a linear combination of two solutions. Because it's a linear problem. But you can also interpret this as what's called a pencil of curves. The pencil of curves, and so for H is 0, you get pencil on the left-hand side. For H 1/3 in this picture, so don't follow that. Then for H equal to 1/3, we get the pencil on the right-hand side. So H is 0. This is the picture on the left-hand side. And H equals 1/3 is the picture on the right-hand side. Then within each picture, now van beta can vary, you get the various curves within that picture. Yeah. So I think this is very nice because, of course, that's a very standard way of very geometric way of thinking about pencils and how this comes up. Of course, if you have more than two, there's a different name. But of course, if you have three, then you get this alpha plus beta plus gamma and so on. Well, in this case, we're in 2 dimensions. You can't have more. Of course, you cannot have, let's say, in 6 dimensions, you can only have 5 integrals if there's any motion going on. And also, yeah, first of all, this is an ansatz. So later on, I'll show some theorems. In some cases, yellow as ansatz, and that may not always work. And then, if your integrals, for instance, are not rational or powers of rational functions, then it becomes very difficult. It's impossible to find it this way. This is all built on algebra and polynomials and so on. Yeah. And also, we're talking about two different things. So the cofactor 0 is for the differential equation. So there, the question would be: is the divergence automatically 0? That's the preserved density, and that's either the numerator or the denominator of the map. Sorry, the cofactor. We did work this out in the general case. So now go to the second part, and now I'm going to have the second example. Here, so this is my 3-dimensional example. Just happens that the first example is 3-dimensional. But here we actually are going to have a much more interesting factorization. So do the same thing. You do the Haan, you have to make the Haan map. You have to go to determine it. It turns out that the numerator will have 4 factors. Here, K1 to K4, and the denominator has 2 factors. So now the question is, so now again, we're going to look at all the various combinations of these. I guess one of them is going to be the Jacobian itself, because you want to know if there's a preserved measure, but also various. And here is 5. In this table here on this place, on this slide, left-hand column, we have the discrete cofactors. In the right-hand column, we have the continuous cofactor, and in the middle, we have the Darboux polynomials. And the Darboux polynomials, you see here, don't depend on h, so they're the same. They're the same for the differential equation and for the discretization. Now, that is not a coincidence. That is because they are all affine, so they're just linear plus a constant. And show the theorem that says the differential equation is affine. That's the same. This is something that we were asking about earlier. So here, actually, so in this case, we have 4 different cofactors in the left-hand column: K1 divided by D2, K2 divided by D2, K3 divided by D2, and then K4 divided by D1 and D2. And for each of those, we found a Darboux polynomial, and then I haven't written out from the previous slide. You can, of course, substitute what K1 or what the Ki's are, and that's very complicated expression. However, it turns out the continuum limits are very easy of the cofactors. They're written in the right-hand column, so they're all very similar. The first one is z, then the next one is z minus 3. The third one is z minus 1, and the last one is z minus 2. So that means that if you take the ratio of, say, P1 and P2, then the cofactor in the continuous case is going to be C1 minus C2, and that's equal to 3. So that means that the derivative of P1, the time derivative of P1 divided by P2 is going to be C1 minus 2 times P1 over P2. So P1 over, P1 over P2 over Q, you get Q dt equals 3 times Q. So Q is equal to constant times P to the 3t. And similar for if you take P1 divided by P3, you get e to the 1t. You take P1 over P4, you get e to the 2t. So that is actually nice. So we get 3 time-dependent integrals that are written down here. Of course, you could choose here. I've taken the denominator always the same. Sorry, the numerator always the same. There, the denominator. Or the ratio of any of those for 2 out of 4, any 2 out of 4, and then of course only 3 of those ratios. But that also means that if we now eliminate t from the right-hand sides of equation 15, 16, 17, we actually get integrals that don't depend on time. So that's very exactly equation 18 and 19. Now, of course, they are not unique because any combination of I1 and I2 is also going to be a bit random how to choose this. But the upshot is that we have a 3-dimensional differential equation with 2 integrals. That makes it. And on top of that, also it turns out that it's measure preserved. So now here, these 2 integrals we found in 18 and 19 are both rational functions. And remember, my sort of mantra says polynomial is good, rational is bad. Polynomial is easy, rational is difficult. I challenge you to find those integrals just from looking at the differential equation. And in particular, I challenge you to find the preserved measure just looking at the differential equation. Again, the preserved measure is also not unique. But, this example I'm giving now just a special case of a much more general equation where the result is still quite similar, but where it would be even more difficult to find these. And so that is how it would work generally if you have a, if you're lucky enough that everything works. Actually, in this particular example, there turns out to be even a little bit more. Because if you look at the equation 15, 16, and 17, if you look at the middle column, for instance, the first one says z minus y minus 3 over 2z plus y is equal to e to the 2. If I move the 2z plus y to the right-hand side, I'm going to get a linear equation in y and z, with coefficients depending on time. And if I do that with all 3 of them, I'm going to have 3 equations, 3 linear equations in x, y, and z. So we're going to have 3 equations in 3 unknowns, and we can solve that. And I should stress that is particular to this system. So this is not something actually this is trust. So you can solve that. You actually here we have the explicit solution of this non-linear differential equation. So it's expressed in terms of three initial conditions, K2, K3, and K4. You can express them, of course, in terms of x times y. The fact that you can do this in this case, I think, is significant. 5 minutes. Yeah. Okay, that's on perfectly on time. So the only, yeah. So now I'll show you that. Well, I've mainly talked about two main examples, but some people prefer theorems to examples. So here are some theorems. So the first one basically says that if the differential equation has affine two polynomials, then the Kahan equation has the same. So that's the second one. It's the same. So it's not so strange that we got that example. Theorem 2 says that we have already been able to do 4 dimensions. Is that affine the differential is an affine Babu polynomial. Basically, it says that you can find it in this way that we did as a factor of it. It's just expressed in terms of the numerator, but I think we proved the whole thing is a factor. Now, that proof says it's not very good. It's not hard. Just wrote down general case. One little trick, then all the coefficients, and then just make it all work out. So those two, theorem 1 and theorem 2, basically explain three-dimensional example in the second half. Then theorem 3 says if you have a cubic Hamiltonian, and now in any dimension, then that is discretization as these two the cofactor and the codeterminant. Now we're talking about any dimension. H is Hamiltonian, and A is A of x is 1 minus 1/2 of H times the vector. H AD J is the aggregate. So it is a complicated expression. And again, this was found originally by really hard work. Of course, now find these things. Of course, with Maple, you always find examples so to find such a general expression in any dimension. There still you need to do a lot of these special cases before you can get the form correct. Here. And then, well, here's a summary of the whole poodle, if you like. We have to start with the quadratic differential equation, like the Kahan map, but there finally I have my explicit expression for the Kahan map. You see that the same 1 minus h over 2f prime appears there as a denominator. This is a coincidence. You can't see there so easily that it would be by rational, but actually I think the universe is taking x and x prime and h. Okay, so you got your Kahan map. You can compute the Trobe determinant. factorize that. Then you try all factors of K. Well, usually, after a while, you build up some sort of intuition about which factors are the most likely ones. So you try that first. And first, let's say we have no sort of affine double, we don't have proof in all dimensions that these always work. But we certainly have a trajectory that is the case, at least for affine. Then we do take the continuum limits. And so for P, just take the limit the h goes to 0. And then for C, actually it's slightly different. And you take discrete C, subtract 1 and then divide by h. That's the definition of slightly different. And then you can construct it once you found integrals. Once you found the taboo polynomial, you should construct the integrals as products, powers of the taboo polynomial. Similarly, with the measure, subject to finding that 0 or so that is it. References, and of course, I'm very happy that the SMRI supported my visit here to the University of Sydney. And so here are some references. First, there's a few for discrete double polynomials. Actually, this Spanish group, they were the first to Azul and Mendoza were the first to write something about discrete. We don't use this decoding in their conjecture. And then on the maps that we call for ODEs. Orieli's book is a very good source for that. And here's some references on Kahan's method and some references on generalizations of other variation methods. And we found these two. They have the same cofactor, so their ratio is the integral. That's their ratio is going to be the modified Hamiltonian. And if you just have one of them, it's 1 over P1 or 1 over P2 is the preserved density, the density of the preserved measure. Or actually even linear combination, which have freedom in the distribution of density. Let's say Hamiltonian system in n dimensions, integrable. So say 2 n dimensions, with n integrals. But any function of those integrals times the preserved measure is still a preserved measure. Actually, you actually have fewer in the discrete. Well, the way it's slightly different. It's similar. You don't get exactly the same things. Martin, would you like to pose your question?
Oh, now I can hear you. Thank you. Hi, Reinout. Hi. About the Kahan map. So you said he worked on it like for 25 years or something like that. So he only worked on quadratic maps, and I'm a little bit confused on that one. And my second question comes with it. What would be known if you assume it's integrable? You make it near integrable, so you make a small perturbation. What would you know about the Kahan map? How would it still work?
So Kahan's method only works for quadratic differential equations. Now, I don't know if he used different methods for other equations or that he was particularly interested in quadratic equation. The reason we worked mostly on that is that it's, in a sense, is the simplest case and was already hard enough, in a sense, to keep us busy for quite a while. But these other methods that I mentioned at the end, I say they give, and actually our polarization method, which we published not much later, that works for first order systems of any degree. But then there's some technical complications there. In a sense, the work with Hone is closer in spirit, and there you have systems of degree D and order D minus 1. So for instance, in particular, you can look at cubic equations or systems of second order cubic equations, which are of course very important in applications. But much less work has been done on this, so it's still a new field which we're sort of trying to explore.
There are a few people who claim at the moment that they can do more general ones, but I somehow doubt that this is actually correct. So, because when they claim they're using Kahan's method, I think one has to say that it is.
Oh, well, that I don't, well, maybe I should talk to you in more detail about that sometime. I'll come and find you sometime, or get in touch with you. Yeah, of course, some people, you are right. Not, let's say not everybody is always equally rigorous, especially in the, well, no, I shouldn't say. Shouldn't specify that too much.
No, I just mean,
but not everything that is claimed is correct. But certainly Kahan.
Kahan is for quadratic ODEs. That's
yeah. But Kahan, the interesting thing, because we asked Kahan why he had defined his method in this way, so that, for instance, is linear implicit, and that was basically because he did his computations on a pocket calculator.
Yeah.
In those days, and so it's very important that you had something that was not implicit. And still he got a long way with his pocket calculator.
Yeah. No, it's very simple, so it's great from that point. Yeah. Thank you.
No worries.
I was just wondering, if you would say it's more like the classic question of near integrable. You have an integrable system. Suppose you have like your discrete method is working. Now you have like a small perturbation, so it's near integrable. Now, for a continuous system, it's always easier to make statements, but for discretized system, it's not clear how far you would get with your solution before you start to diverge. So I just wondered what is known about basically like the discretized near integrable versions. I'm not, so familiar with that.
Well, I must say, I don't think much has been done. What we have done is some work on finding, let's say, the integrable ones in a family, or finding special parameter values where there are additional Darboux polynomials and so on. But usually that's so those are, it goes the other way, that you specialize. Now I think with the perturbation, it depends a little bit how you perturb. Just something that the fact that something is a small perturbation can still destroy all the structure of your differential equation. If you destroy all the structure, then you're not going to, then none of the Darboux polynomials are going to be left.
Yeah, correct. Because I meant more like, because you mentioned at the beginning, which was interesting from a point of view. If you think like continuous, if you think continuously, then you can actually get to infinity. For the discretized system, you have a pole based like on 1 on h, based like that radius. So you have a 1 on h radius for the discretized system. Now the question would be like, how close can you get to that basic like radius, depending on.
Okay. Oh, like that. Well, I have looked a little bit at that. I don't think we've published anything about that yet. But there, let's say for that example that I gave, there was sort of a circle. Now, if you are within that circle, it depends whether your so-called base points are, let me see if it was something, but let me show the picture here. Yeah. In this picture, if you're, this picture, these triangles, they are fixed. So they are there for any value of h. Yeah. Now, if you make the h very small, then this circle is actually going to intersect with the triangle. So then the triangle is, in a sense, is lost, because then you can move out of the triangle. But as long as the circle as the whole triangle is inside the circle, what happens inside the triangle, as far as I can tell, if you are starting there, you stay in there, and everything is sort of on a close. But if you outside that triangle, you see there are curves there, and they probably go off to infinity from memory, and so they will intersect the circle somewhere. Then you map to infinity in one fell swoop. So it's then it's not so useful as a numerical method anymore. I must say here in the study of this, I've looked more at the discrete integrable systems kind of things than at the numerical properties per se. Yeah, but certainly it'd be nice if we can find an opportunity at some stage to talk about this in more detail.
Thank you.
John, I guess one of the nice things is that these lines, they are affine. The lines of the triangle, they are affine Darboux polynomials, so they're always preserved. So if you're inside them, you're inside them, whatever the curves are like. Yeah. May not be able to find the curves, but you're still this area inside the triangle is stable. Yeah, well, I guess they're all legitimate questions, and to some extent, it's also for some purposes, some things are more important. So also these geometric, all these different properties. Measure preserving, and then measure preserving up to a constant, and so on. Yeah, so they each have their application. And sometimes, if a differential equation has two conflicting properties, then you have to choose one or the other. Yeah. Okay. So it's been going for quite a while.
Let's thank